My name is Thompson. This is Nolet. So anyway, we're here to talk about GPU-enabled data science. My role at NVIDIA is I'm a senior solutions architect. I work on a federal team, and I am up here in Maryland all the time. My background is actually in signal processing, so I do a lot of signals work, and I've been touching GPU programming on and off since CUDA Toolkit 2, which is around 2009, 2010 timeframe. I went to Clemson for undergrad and Georgia Tech for grad school, so go Tigers. And then Corey, you want to introduce yourself?
Yeah, I'm a data scientist and a senior engineer on the Rapids machine learning team. Before NVIDIA, I spent about a decade scaling exploratory data analysis software on HPCs for the defense industry. It's actually how I know some of the folks here. And I'm currently working on my PhD in computer science on unsupervised representation learning methods and scaling them.
Awesome. So if you have any questions, we can make this as interactive as possible. So don't hesitate to raise your hand and sort of poke at either Corey or myself. If you've seen a couple NVIDIA presentations, I always kind of like to say it's not an NVIDIA presentation unless you have some form of this chart, which is essentially talking about CPU performance over time with respect to GPU performance. And so traditionally in the era of CPU compute and Moore's law, we were getting a 1.5x speed up every year. So performance would double, essentially every 18 months. And so one of the nice things to do is if you have a type of process that you want to make faster, the way that you solved your problems, you just waited, you did nothing. Because you knew that in 18 months, Intel was going to release another chipset and your processes would automatically be faster. So this has sort of started to, that slope of this line has started to degrade in the last few years. And this is a lot because of physical limitations. You're having a hard time putting as many transistors on a wafer. You have problems with heat dissipation. But fundamentally, you have something that is based on CPU, which is latency optimized, meaning that CPUs are, you're pushing up clock speed. So what you want to do is you want to have information being processed as quickly as possible in serial. GPUs, on the other hand, are throughput optimized. So the idea is how much work can we get done at once. And so a common analogy that I kind of like to use, and sadly this isn't my own, I saw one of my really good friends said this, is the best throughput versus latency argument is how you carry in groceries from your car to your house, right? You don't take like 2 bags because you can walk faster to get into your house. What you do is you grab the entirety of what you bought at the grocery store in your 2 hands and you penguin walk to get home. So the idea here is that you're trying to get more work done as possible in sort of the shortest amount of time. So one of the things that I do like to mention is, if you ask somebody on the street, what does NVIDIA do? They would say, well, they make graphics cards so that I can play, my favorite computer games, video games. And then sort of around the 2010s, if you asked someone in, kind of these niche little circles, what does NVIDIA do? They would say they're a supercomputing company, right? They're used and they're put into, GPUs are put into some of our nation's largest supercomputers to solve really compute-intensive type tasks. And now, if you just woke up and someone said, what does NVIDIA do? You would hear the AI company, right? So we have to think about what bonds together displaying pixels in computer graphics to high-performance compute with being in Summit and Sierra and some of these, the nation's and world's fastest supercomputers, to artificial intelligence. And so I do like to talk about the history, right? So delivering pixels, so just the process of taking a 3-dimensional model and projecting it onto a 2-dimensional image and putting color is a really compute-intensive process. So the way this works is essentially you have a 3-dimensional model of the scene that you're trying to visualize. And it is modeled with overlapping polygons, triangles, that form essentially what you're trying to project onto 2-dimensional space. And these vertices of these polygons contain important information like the position relative to the scene, what your color is, what your texture is, etc. And so you do a process called rasterization. which is when you project information from this three-dimensional model with these polygons onto your screen. And so if you think about, a 4K HD video screen, that's 8 million pixels. So what you would not want to do is to do this serially and start with, your very top left pixel and say, well, essentially, what color should this be? And then, when you move on to your next one, you say, well, what color should this be? So the graphics card was actually invented to do this operation of rasterization in parallel and at a speed that is updating, every 30 to 90 times per second. So it's getting, you're not seeing like visual lag and you're seeing detail. And then moreover, after the process of rasterization, you have something called shading, which is when you're doing local sort of associations to see how light interacts with the scene, to see how shading works. So again, you're seeing all of these really compute-intensive parallel processes. So that's sort of the pixel delivery part. And then around 2006, 2005, 2006, some of our engineers invented a programming language called CUDA. It's actually an API to C or C++. And the idea here is, fundamentally rasterization and shading is just matrix multiplication. So can we put in math that we care about, and instead of getting out a pixel value of an RGB sort of color or a texture or something like that, can we just have this show a number that I care about, right? So this is sort of the evolution of it's the evolution of dense linear algebra that is being performed on GPUs through this high performance compute. And so the signal processing community adopted this really quickly because you could really accelerate fast Fourier transforms in this space. You could look into spectral estimation techniques really quickly on GPUs and really just decompose everything, which is essentially a matrix solver or a matrix multiplication or something else that's highly parallel. And it works really well on this GPU construct. So finally, going to deep learning, what is deep learning in terms of neural network training? It's just matrix math, right? So in the process of backpropagation and gradient descent, all you're doing are just matrix products. So the difference between delivering pixels to doing high performance compute to doing AI is not sort of as crazy as it may seem. And it sort of tells the good story of the GPU. So if this heady thing right here, so this is our V100 for show and tell. I'll pass it around. You don't have to worry. It doesn't work. So I'll pass it around. So this is a data center GPU. It's the PCIe version. So if you've never seen one, that's what it looks like. There's another form factor which can actually be mounted to a motherboard. But this is sort of the one that people are most familiar with. So going back to latency optimized versus throughput optimized, one thing to remember about GPUs is that since GPUs are throughput optimized, they're invariably latency hiding. So in my example of GPU versus CPUs of getting groceries out of a car, what you want to make sure when you're programming and deploying GPU solutions is to keep the GPU fed with as much data as possible. So while the GPU is being fed with data, you're doing processing on the GPU and doing your math and doing your deep learning training and all that other good stuff. So what we want to avoid is data movement onto and off of the GPU if there isn't computation going on it at that time, mainly because that is the bottleneck in the processing. Yeah, question?
So your vertical axis is exponential. So what we have here is an exponential on your lines.
Yes. Yeah, so this is essentially saying that this is getting into something that as we increase parallelization, so it's the difference between latency and throughput, because what we're saying here is that when we ultimately look at CPU optimization, it's increasing clock speeds, which we're not really able to do much anymore, but we can add more parallelization through more CUDA cores and doing more work at once. So another thing that's sort of fueling the deep learning and machine learning revolution is this idea of an exponential growth in the amount of data we collect. So we know that the companies like Facebook and Google and all of those big data companies in the world have massive amounts of data. And then as IoT devices come on board, there's even more. So we can see this growth. So this axis right here is exabytes of data. So there is a need to start to apply machine reasoning to our data so we can better make decisions, not only as consumers, but also as a country. So we're going to get into machine learning a little bit here. And the idea is that machine learning traditionally is kind of a clunky workflow, right? So if you're dealing with the traditional big data, the big data ecosystem, you kind of have a couple major sort of tasks to do. There's the data management, which is in your ETL. You have if you want to do machine learning, we have our training component, and then we need to evaluate our results via visualization. So this is looking at matplotlib and all other types of charts and graphs. And then ultimately, if we get something that's working well, we can deploy it via the process of inferencing. So this is saying, let's make new decisions based off of the models that we have previously trained. So one of the issues here in terms of dealing with this workflow is this typically takes a really long time. And then you could have a process where your ETL job fails, and then you're sort of stuck. So what Rapids and sort of the bulk of Corey and mine's talk is trying to address is let's put this entire workflow onto a GPU and accelerate it while reducing data movement, which is a key of sort of the applications of a parallel processing paradigm. So again, going back to, this is sort of a cartoon looking at the day in the life of a data scientist. So pardon, I'll point out some of the misspellings. So this actually, we had an engineer that sent this to our CEO, and he included this in his keynote in Europe last fall, and he kept the wonderful misspellings and all. So you've got like config U and decaf. But anyway, the idea here is that we sort of have this CPU-powered workflow where data science is really, it's not to the point of being speed of thought. So what we're doing, again, is you start in ETL, you say, oh my gosh, like if I just added this feature, then maybe my experimentation would have been better. So then you restart your workflow, you go grab a coffee. So anyway, these green color-coded are you not doing work or getting a coffee or looking at ESPN or whatever you do. And the red parts is when you're actually doing real work. And one of the things, from living, kind of this life, one of the things is that when you're doing experimentation, how many times have you started to, train a model and you kind of like forgot what you're doing, 30 minutes later. So the idea, and this isn't where we're at now, but this is where we want to be, is to have this all GPU accelerated to make data science speed of thought. Meaning you say, I want to look at this new feature, I want to try this different model, and you get instantaneous results. And so if any of you are managers, we like to say that the red parts are what you're actually paying people to do. So if you're paying people salaries, you want them to actually be doing work. So another sort of motivating factor here for a GPU-enabled workflow. So some of the traditional GPU adoption barriers, and we see these sometimes within our ecosystem, is data movement is the bane of GPU compute. What you absolutely do not want to do is take a small data set, move it onto the GPU, do like one matrix multiply, and move it off. That's probably, if the data set is small enough, you're probably going to be faster on CPU because it's not making use of the latency hiding nature of the graphics card. There's also, in terms of the big data ecosystems, there's a lot of makeshift data formats, right? So you have HBase, Cassandra, you have pandas, you have CSV, you have JSON, you have all of these different file formats. And then, if you look into GPU computing, writing CUDA with C and C++, it is kind of hard, and it takes some real skills and real ninja abilities to go in and look at profiling and seeing how you're achieving optimal concurrency, which is essentially moving data onto the GPU while doing processing and making sure you're not hitting any significant computational barriers. And then finally, there's no well-known and well-understood Python API for any of these data manipulation tools. So again, these slides are basically emphasizing the fact that what we want to do is stop this data movement between the CPU and the GPU. So in our Rapids work, we leverage the Apache Arrow standard. And so what Apache Arrow is it's an in-memory, columnar way to represent data. And so the idea here is that if you were going from one of these formats to another, you typically had to copy, so that's a data movement, and then convert to, between CSV and Parquet or whatever you were doing. So Arrow memory is cross-language support and allows all of these different data formats and applications and databases to speak Arrow. So one of the nice things here is it's columnar stored. So that means, if you're thinking about an Excel spreadsheet, if you have names, ages, and sex of an individual, you can say names are strings, ages are ints, and say the sex, male or female, is a character. And so if you store something via a row, you have to store 3 different data types. But if you store something via a column, you know the data type, in terms of accessing that data format from storage or from spinny disks or wherever. It's going to be more computationally efficient if you know how the data is represented. And you can also do compression on it easier because it's all the same data type. So, fundamentally this is building the case from looking at Hadoop processing where you have slowdowns with the Hadoop data file system read-writes, going down to Spark, which got some speed increase because you're doing everything in memory. And then, kind of the intermediary before Rapids was, well, let's move data onto and off of the GPU. And that was a little bit better, but it was, kind of kludgy because you have all this data movement. And so now with Rapids and what Corey and I are talking about today is fundamentally we're leveraging Arrow to keep everything on GPU. So that's what Rapids is. So Rapids at its core is 3 major libraries. It's all open source. You can go to the GitHub. We'll talk about it a little bit more here in the talk. But it's essentially you have cutie, which is the data frame, sort of data wrangling component. So this is meant to be like pandas-like. You have QML, which Corey is going to talk about here in a little bit, which is a scikit-learn-like library. And then you have cugraph, which is meant to be like network X. So the big things here is doing data exploration, machine learning, and graph analytics within sort of same GPU-enabled ecosystem. So it builds on top of the CUDA architecture, and you can really get Rapids wherever you feel most comfortable. So if you really want to dive into the weeds and you're a C++ CUDA person, you can get Rapids there, or you could get Rapids at and deal with these data science problems at the Python layer, the higher sort of data scientist aspect. So again, I preempted myself a little bit here, but this is essentially what Rapids is trying to do, and some of these are already implemented here. But one of the neat things is that you can do your data exploration, ETL, and all that other goodness with cuDF, and then progress within this chain, again, all in this GPU Arrow in-memory ecosystem. So you could even port to deep learning frameworks that are compliant with this array interface that is PyTorch and Chainer. And then we can look into some visualization as well, not only with something like matplotlib, but you would have to transfer that to CPU for that at this time. But Kepler-GL is a nice tool for accelerating some visualization. So this is building on here. One GPU is good, but we would also like it to scale not only to multi-GPUs, but multi-nodes, so dealing on ever-increasing data set sizes. And we leverage Dask, which we'll talk about here in a second, for parallel scheduling of Python APIs that's all based here. So again, this is sort of just a visualization of the entire software infrastructure that we're using to create Rapids. And again, cuDF is meant to be pandas-like. So they're striving for, the team is striving for 80% compliance. So the idea is if you have pandas for a traditional, your experimentations at work or at home, instead of saying import pandas as PD, you could say import cuDF as PD, click run, and 20% of your code you'll have to look at, right? But that's what PRs are for on the GitHub. And then QML is supposed to be, scikit-learn-like. It's the same thing, 80% compliance there. And QGraph is network X-like. So just a quick view into Dask. It's a distributed scheduler. So the idea and why it was sort of even came about is Python is sort of the language du jour, right? And it's the one that folks are really liking, and it's easy to learn. But it sucks, honestly, at sort of scaling out. And so if you program in the Dask ecosystem, you can easily scale from your one GPU on your laptop to multi-node, multi-GPU on a supercomputer with just a few changes. So Dask, we actually have the lead developer of Dask working on the Rapids team, and so improvements into merging this ever increasingly more intimate with the Rapids framework, and then also making it even easier to use is a big priority of the Rapids team. And this also works over our own sort of infrastructure. So NVLink is our own interconnect, which is targeting single node tightly coupled GPU systems. And then as you scale to multi-node, you have some RDMA, which is the remote data management access, or data memory, the remote direct memory access. And then InfiniBand, which is RDMA over Converged Ethernet. So basically what this means is that there's support of if you put together multi-GPU clusters that you can have, you can optimize data movement with the low latencies of these network fabrics. And then actually putting some numbers in front of you guys. So here is a chart showing data load. I'm not going to, I'll let Corey talk about his QML stuff. He has a slide later on too, so I'm not gonna beat him to the punch. In terms of QDF, data load and preparation, so this is a 200 gigabyte CSV data set. And you can see here with 20 CPU nodes, we're at around 2,700 seconds. With 100 CPU nodes, it's 380 roughly seconds. And with 5 DGX1s, which is an 8-way GPU server, that's 19 seconds. So you're seeing this massive speed up in terms of just reading in a CSV data file. And then we're seeing the same type of performance increases on the extreme gradient boost. And then finally, the thing that's really important is the end-to-end processing. So, doing the ETL, doing your transforms, doing your machine learning, so the entire workflow is significantly faster. And here at the end, I actually have a notebook which is showing DB scan performance. And so we can step through it. It's going down to my workstation at home, so you can see these speed increases in real time. So looking at, sort of, again, this is an overview of the tools, and I'm not going to go into the machine learning aspect too much because Corey has a whole section on here. But fundamentally, we're seeing just massive speed ups in these particular tools that we're using, and these particular algorithms that we've implemented already are continuously being optimized, and also will be more features will be added as time goes on. So going into QDF just a little bit so you can see some relatively simple examples. Again, I mentioned earlier that QDF is trying to be, mimic the pandas API. So you can see here, this is just read CSV, so pretty simple, right? But again, you can see, it's the exact same code right here. So the difference between the PD, which is pandas, and QDF is a pretty simple way to get started. And this is, just to prove, this is a GPU data frame, so it's pretty similar if you've seen pandas, right? So the output is really familiar and really friendly. And again, you have some of the major elements of pandas that you use for a lot of data science. So you've got filters, You can do ufuncs, you can do joins and merges, all different types of good stuff. CoostString, so string support is actually really hard on GPU, believe it or not. This is some initial benchmarking with CoostString and NVString. So anything, we like to have CU for CUDA, so anything that you see is CoostString is sort of the Python-esque wrapper around the NV library, which is all CUDA. So we can see here with some of the string operations, so low refined slice, that we're getting some pretty significant speed ups on early testing. And again, this is one of our big areas of focus within the Rapids team, is making sure that string support is really effective and really efficient. And again, this is essentially saying that while our accelerated data loader is CSV right now, we're currently working on Parquet and Orc, and more data formats will be added. So, it is to say that if you went to get Rapids right now, it's version 0.5, which is still really new. So one of the nice things, and this is sort of the call to action of this group, is to get involved in the community, right? So you can pull the code, it's all open source, so you can add to the documentation, you can issue pull requests, they love pull requests, you can issue an issue, and these guys in the Rapids teams are really good and take the GitHub issues and comments very, very seriously. So it's a great ecosystem to be involved in, and you can sort of shape it to the problems that you care about. And then one final word on cuGraph before I turn it over to Corey to talk more about cuML. We have previously had some graph analytics tools, so this is PageRank, triangle counting, those types of algorithms that were implemented on GPU via NVGraph. But again, that was just accessible via C and CUDA. And so the effort with Rapids is putting Python bindings around those, so you can call them from Python, underpinning again this in GPU memory Arrow ecosystem. So these are just some standard graph data sets, and this is running PageRank on it with one GV100, which is one of the Volta V100s that I passed around. And you can see the speed up versus network X. You're getting anywhere from the hundreds on this data set to on the Hollywood data set in the almost 10,000 speed up over network X. And some, going a little bit more of looking at a relatively small graph, so 5.5 million edges, 51,000 nodes. In Spark, it took 172 seconds, and on one of those V100s, 671 milliseconds. So we're looking at 256x speed up. So again, PageRank is something that is really easy to parallelize and to accelerate. So as we find more applications like this, this is really sort of the type of problem that is well positioned to GPU. And one thing I would like to add here is on a single GPU, so again, this was a V100, this was 100 billion traversed edges per second. And we're thinking that we can reach around 300 billion on MG multi-GPUs, so 4 GPUs. So starting to look at really sizable graphs that have meaning to certain folks on this side of the river. So with that, I'm going to pass it over to Corey for cuML, but pause if you have any questions. Please don't hesitate to ask.
Sure. Are there any questions about this stuff?
You said it worked with deep learning frameworks like PyTorch. Does it also work with TensorFlow?
Not yet, because TensorFlow doesn't support the array interface type. So you would have to do some. You could essentially you would get you could save off, convert to like a NumPy, move it to CPU, and then you'd be good to go. But keeping it on GPU, no, not right now.
Do you have CPU implementation of this or only GPU?
So the question is, do we have CPU implementation of this or only GPU? So to some extent, my response would be the CPU implementation would be pandas, or would be scikit-learn, or would be network X. So we'll show here, towards the end, we'll show a direct comparison of dbScan, which is using, the dbScan that's in scikit-learn versus the GPU-enabled version of dbScan, which is in cuML.
when you say it works with PyTorch, how exactly do you pass the things? How overflows?
Yeah, so the PyTorch integration is still ongoing,
Okay.
but the idea is that Python accepts a numerical data type called array interface, which is leveraged within Arrow and Rapids. So essentially, it is the PyTorch folks have accepted this data type into their framework, so that you can have a sort of a flawless transaction between sort of the data science on that
Right.
workflow. So,
How do you translate it into frameworks? I mean, I start with what?
So that array interface actually allows you to take the pointer to the device memory, and it transfers it over to the PyTorch API, back and forth with ours. So without having to copy the data, you're literally allowed to reference that pointer in memory.
So in one line of code, I call, for example, one thing and then just passing it to the PyTorch,
Exactly.
for example?
That array interface is what defines the data structure around that pointer, so that you can create that PyTorch object tensor or create our own pandas objects with that. Kind of go back and forth as you need. If there's no more questions, I guess I'll get started. I want to kind of set up the problem that we're trying to solve here. Right? The problem is that data sizes aren't getting any smaller. They're constantly growing, right? I mean, you've seen all the charts. We've talked about big data. We've been doing that for years. They're compounding more and more and more and more. The more we're realizing what we can collect and how fast we can collect them. Right? And as we're kind of beginning our data science process and our data exploration process, anybody that's trying to model data is always faced with this problem of model complexity, right? You have too complex a model, you're not going to generalize well when you're actually trying to use the model to ask it a question on data that it's never seen. If you have too simple of a model, it's not going to learn the patterns that it needs to learn. I'm sure you guys have probably seen charts like this before, overfitting and underfitting. You want to try to find that spot right in the middle that's, kind of equally good. It can give you the best prediction it possibly can, given the different types of data that you have. Back in 2009, the director of research at Google had released a paper. His name's Peter Norvig. He released a paper called The Unreasonable Effectiveness of Data, where he was working on the language translation models for Google. And the paper basically says that having more data can act as a regularizer, right? It can stop you from overfitting. So we're faced with the problem of adding more data, right? Fortunately, the other problem, when you're trying to stop yourself from underfitting, you end up adding more features to your data. Again, you're adding more data, right? You're making bigger resource needs in order to solve your problem. You can't start with the small data, right? You have to start with the big data. You have to start with as much as you can, figure out the distributions that are important for your problem, whittle your data down to something that's manageable, and then get your model out of that, right? So I start with the beginning of this funnel here with my massive data set, right? I might create some histograms. I might try to model some parametric distributions to see what I can fit the data to, looking at the different distributions of features. I might reduce the dimensions in some ways. I might try to do some latent analysis to see if I can create little clusters. I might do some feature selection, remove some outliers that are really pulling my data in one place or another. I might sample the different samples of data. At some point, I'm going to get a model, right? That model's probably not going to be right the first or the second or the third time. I'm going to have to iterate. If I'm lucky, I have some type of labels or something I can use to cross-validate on different scores. I'm going to do some grid searching. I'm going to iterate some more. Before too long, hopefully, I'm going to get a reasonable trade-off between the accuracy of my model and the cost of having to run that model inference on my system, right? Time's increasing through this process, obviously. It could take me, what, hours, days? It's taken me weeks before. The more data requires better approaches. I lifted this from this CTO of Cure AI. It's very true, right? We scale out with these CPU infrastructures, causing more need for power, space, and cooling, for diminishing returns. Whereas what we're demonstrating on GPUs is that with a lot less need for power, space, and cooling, we can have significant speed ups with a single DGX, with 4 GPUs, with 8 GPUs, with 16 GPUs. So I'm going to kind of brush first into the real high-level view of kind of what cuML brings, where you plug in, how you would use it, and I'm going to kind of dive a little bit more into the lower-level details of the architecture as we go. Feel free to ask questions, by the way, as we go. I kind of want this to be for you guys. So, as Adam pointed out, obviously at the very top layer we have Python. We're trying to appeal to the data scientists to make as minimal changes as possible to the notebooks that they've already been writing in their CPU infrastructure with pandas. But underneath Python, really what Python is doing is it's calling down to C++ algorithms. That's really where the guts live, right, is in the CUDA kernels that we write, that we're exposing into the Python layer. But we also provide the hooks for your engineers to plug into that layer. Way down underneath the actual CUDA libraries, we also expose for anybody that needs to plug into them. There's a lot of CUDA libraries that perform different purposes. We have sparse libraries, we have random libraries, we have libraries for doing the matrix multiplication. Now we're presenting the libraries for doing dense operations on feature matrices, which is what machine learning is all about. So these are the reusable building blocks that you would use to build the algorithms, if that's all you need from us. The primitives layer, it comes as no surprise that linear algebra makes up most of that particular library. But we also provide statistics packages. We do have some sparse matrix operations that we provide. It turns out it's, if you can put things into a sparse matrix, it can save a ton of memory, make things a lot faster. Randomness is really hard to do on a GPU in massive parallel. So we have libraries to do that as well. Pairwise distances and metrics, optimizers, stochastic gradient descent, elastic net, LBFGS. We've got all those packages involved in our primitives. And then obviously the algorithms that live on top, as Adam pointed out, we're eventually trying to replace the entire thing. But we've started with the algorithms that give you the biggest bang for your buck. They're the most effective at covering the widest set of problems that need to be solved. So we've started with linear regression, more generalized linear models. We've started with clustering algorithms. The two most common that you find, kind of opposite extremes, k-means and db-scan. We're going to be adding spectral clustering here soon. As far as decomposition, dimensionality reduction, more linear models doing the principal components, singular value decomposition. UMAP is working its way in there as well. We're planning on adding time series forecasting, which is something that sklearn does not have a whole lot of. So you also find kind of, we're not just trying to replicate what's there, we're also trying to add the other necessary components that data scientists need. We're going to be adding recommender systems soon to kind of match what Spark has with their distributed recommender system, the implicit matrix factorization. We're working through a distributed hyperparameter tuning, obviously providing the cross-validation to be able to provide that. So kind of diving down a little bit further, but still keeping somewhat high level, as Adam had kind of described to you what Dask is the role that it plays within this ecosystem. Obviously, we have cuDF that can make use of Dask so that we can do distributed data parallel operations to be able to load up our data, do our ETL all in massive parallel. But we also make use of Dask on the cuML team. So Dask actually provides a Dask ML library for doing more CPU-based operations. We provide a GPU variant of that utilizes the GPU machine learning algorithms underneath. And that's also scikit-learn-like. So if you're familiar with scikit-learn, you should be able to transfer over to Dask fairly easily and find that it can help you in your multi-GPU training and inference. We're also going to be scaling it out soon to multiple nodes. The obvious separation between Python and C++, you can plug in at the C++ layer. And the idea is for the algorithms themselves to be able to act as standalone multi-GPU and multi-node. Obviously, so that we can be more portable, right? We could put this under Spark, we could put this under Dask, we could put it under some other future framework without too much trouble. So Dask is really focused on more of the data parallelism. Whereas the CUDA and C++ layer more focused on the model parallelism, actually parallelizing the matrix multiplies, parallelizing the eigen decompositions. So here's the technology stack from a different angle, just to kind of show you the general actual technologies involved. The Python living up top, we're exposing all of the C++ algorithms through Python for speed. So the Python layer can obviously interact with the DAS QML, the DAS cootie, everything we're trying to make interoperable in the Rapids ecosystem. But similar to scikit-learn, we also make cootie and NumPy compatible. So that is to say, you could take a CPU NumPy array and pass it into the QML algorithms. It will put it on the GPU for you, perform the necessary operations, and then put it back onto the host memory for you. And then the CUDA libraries that we integrate with that help make QML possible would all be exposed through the QML API. So these are a lot of the libraries that come with the CUDA toolkit. So I'm going to bring you guys through a simple example, not necessarily to kind of demonstrate like technique behind data science. They're very contrived examples, but just to kind of give you guys a hint of the syntax, how similar it is to scikit-learn, and the minimal amount of changes, and then a couple of the differences that we present that are different from scikit-learn, just because we have these new data structures that can reference the underlying data on the GPU rather than having to pull it back to the CPU all the time. So I'm going to start out with loading a data set of Flower, a very common iris data set for testing, very contrived example. But here I'm demonstrating how easy it is to read a CSV. Kind of as Adam had pointed out, I can load that right in, do some simple data frame operations to be able to select the columns that I need. Here I'm just going to demonstrate dimensionality reduction with PCA, a very simple example. So I don't necessarily need the class that I have in my feature set. So I'm going to go ahead and drop that. You can see that when I do a print to the screen, it looks identical to what it would in a regular CPU host memory-based pandas data frame. I'll just do a quick exploration of the variance. You can see here, there's an obvious reason why I chose this example, because I want to be able to visualize what the data looks like. And it turns out that the 97% of the variance is in the first two components, which would be perfect for visualizing. So you can see here, it's exactly the same as scikit-learn. I create my PCA object, I tell it the number of components. In this particular case, I want to be able to explore the variance of the components, so I'm setting it to the number of features that I have in my data set. I call fit, I pass the data frame right into it. I have my explained variance ratio. This matches the scikit-learn API exactly. So in this case, you would just be able to change an import from your host memory-based scikit-learn to the device memory-based QML. Now I'll go ahead and do the actual reduction now that I know how much variance is kept within the first two components of my data set. Do the transform to reduce the dimensions. Down here, I'll just go ahead and chart the data after I've rotated it into the new components. And here you can see I have this as GPU matrix function that I call. This is very similar to the as array function that you would see in a pandas, regular pandas data frame. This is nice. This returns a number array. It's actually a device array. Numba has made this device array to be as similar as possible to the NumPy interface. So you can interact with it just like you would with NumPy. But it's actually referencing the data on the GPU. So as you're interacting with this, it's keeping the memory on there. And I can draw a chart the same way I would with a NumPy array while the data is still on the GPU. So you can see here I've done the scatter plot of my two dimensions that have been reduced. Very simple example.
Where did the plot function? Was that in that plot?
This was pyplot, yeah, the plot function down here, yeah. Just kind of a demonstration that I can have the data sitting on the device in Numba, and I can call pyplot just the same with Numba. So I can go back and forth between the pandas data frame and Numba. Sorry, our cootie data frame and Numba. Quick clustering example. Again, very contrived. I'm going to use the moons data set. The moons have just enough entanglement that k-means doesn't do a good job at trying to separate the data into the two different clusters that it should. So it's a good example for using dbScan. which is a density-based clustering technique for kind of using almost the nearest neighbors approach to being able to find the areas in the data with the highest density. So I'm going to make my moons data set. So one thing to note, you could have kept the NumPy array that I used, that I made initially when I loaded the data set, and you could have passed that right in to the dbScan algorithm. But I wanted to show how easy it is to go from a pandas data frame to a cootie F. So you can see that demonstrated here. I create the pandas data frame, and then I say from pandas into the cootie F. This is what the data set looks like. Two crescent moons kind of entangled. Now I'm going to find the clusters, so import dbScan, same import I would do with scikit-learn. Let's just assume I spent a little bit of time tuning these parameters and found the ones that will fit the clusters nicely. So I call my fit, I call predict, and very simple. Almost no difference from scikit-learn. That's the point. So getting some benchmarks that we've done on our DGX systems. You notice that with very small amount of data, there's hardly any speed up, if any. It's not really until you start increasing the amount of data and the amount of features in the data, you really don't seem to suffer from the cursive dimensionality quite as soon. We have some newer benchmarks that we've been creating for GTC, which starts next week. Unfortunately, I didn't have time to put them in these slides, but we've been able to scale this to some massive numbers on the multi-GPU algorithms. I'll show you that in a moment as well. So using our extreme gradient boosting framework, which is a weak learner decision tree framework that uses an objective function to optimize the boosting. It was the first algorithm that we chose to do multi-node. We just determined it was far enough along, it was worth investing in that first, and it solved the largest amount of problems. So demonstrating a full end-to-end pipeline, this was using a bunch of Spark nodes for the CPU nodes, and then using a single DGX2, which has 16 of those V100 cards in them that we were passing around. It's right there in the front. So you can see in the blue here, we're measuring the ETL time, so the time to load, time to do some joins, pre-process the data. The orange is the time that it takes to actually turn it into the format that it needs to be in order to train the XGBoost classifier. And the gray is the amount of time that it takes to actually run the machine learning algorithm. So you notice right away there's a significant speed up by running this on a DGX2. This is leveraging the Dask framework, so just doing multi-GPU over that single node. And it is pulling the GPU memory back to host when it goes to form the data format for the classifier. There was a reason why we did this. But first I'll show you the multi-node. Also leveraging Dask. This is actually spreading it across multiple nodes now. So it's got Dask spreading data out in the Python layer, and then it's got communications happening in the GPUs in the layer below. You notice that the machine learning portion doesn't have the most speed up in here. Obviously, it's the model parallel is going to be harder to speed up, especially as you start to cross node boundaries than the data parallel operations, which are very prevalent here in the blue and the orange sections. Obviously, being able to do these transformations across multiple nodes, they can be done in massive parallel, whereas the operations that require synchronization underneath could be a little bit slower. But now we can take that copy to host out, and we can demonstrate what this looks like end to end. We've gotten it down to 55 seconds compared to the 1401. You can see that this is only 4 V100 cards as well. This isn't the DGX2. This is the full end-to-end. It's a significant speed up. Imagine being that data scientist that's sitting down trying to do this in real time, and you've got to wait 1,400 seconds each time just to find out that you typed something in wrong, that you missed something, that you got an error. So here's a view with the 5 DGX1s. You can see, again, as Adam had demonstrated earlier, that I'm going to dive into a little bit more, as you start to spread across node boundaries currently, you don't find the most speed up in the actual model parallel algorithms, the algorithms that are trying to parallelize the matrix multiplies. But what you do find is the scale, right? With minimal impact to the speed, you're getting extreme scale. This is huge, right? Because being able to load these extremely large data sets over multiple nodes to get that scale allows you to continue keeping your data inside the GPU, processing your entire end-to-end pipeline without having to bring it back, copy it back to the host. I believe this was run on 32 gigs. No, I'm sorry. This data was loaded on, this was 35 gigs. This data was the 200 gigabyte data set, and as Adam had pointed out, I mean, there's a significant speed up in the operations that you can parallelize up at the, up at the data parallel layer. Not quite as much in the QML with the XGBoost algorithms, but the end-to-end speed up is significant. You look at, you had 20 nodes, the power, space, and cooling involved in keeping those nodes able to process this data versus 5 DGX1s versus 1 DGX2 even. So we've got quite an ambitious roadmap and a very small team, and we are on GitHub. I know it's been mentioned that anybody that's willing and wants to dive in, we try to be extremely accepting of people's needs in the community. If anybody wants to contribute stuff, we're very open and willing to accept it. We want to work with people. We want to work with the community. We really want to build bridges, not walls. So you can see here in the middle, we've been working on some requirements for GTC San Jose, which is next week. So we've got quite a bit that we're planning on delivering. A huge push towards the multi-GPU and multi-node, multi-GPU. So single GPU algorithms, we're getting the primitives together to be able to build them fairly quickly. Now we really want that push towards the parallelization across the node boundaries. So to kind of show you the timeline, this was Q4 of 2018, so we had started with the DB scan, the principal components, singular value decomposition. XGBoost was the first one that we brought to multiple nodes. So this is what we've completed in 1 quarter. This is what we plan to complete by the end of the year. You can see that our graph algorithms are starting to really take off as well. So I'll let maybe Adam help finish this off.
So in terms of getting the software, a bunch of different ways. So first of all, I'm actually going to exit out of this and go to a website. So rapids.ai is probably the best splash page to go to get started. And then you can actually click this well-named Get Started tab. And there's a little cheat sheet that shows you how to, essentially load in data. What are some of the common functionalities that you may need if you're not like a pandas or, QML Ninja. And then further, if you scroll down a little bit, there are a bunch of different ways to get rapids. So it's in the Conda, the Conda ecosystem, so you can just copy and paste this into your Conda environment. There's also Docker, which is nice because you kind of have that isolation there that you get with Docker containers. And you can just pull the Rapids AI container. And then you start up the container, and there's some really excellent notebooks that you can look at to really get started and look at some of these experimentations that we've done. It's also in beta in the PyPy, so if you could do a pip install on it. But again, this is still sort of caution there be dragons here. And then as always, there's source. So again, I would recommend you go to rapids.ai, and if you're interested in here. There's also the GitHub repository is Rapids AI, and so you can see the active projects that we've mentioned here. So you have QDF, QGraph, QML, and if you click on one of these, you'll also see, all of the installation, and then you can look at the active issues and discussions and all that other good stuff. Right here.
What are the actual API library names in the Rapids environment? Is it QDF, QML? Or is there also QGraph? Is that separate?
Yep. So there would be separate GitHubs for QDF, QML, QGraph, DAS QML, DAS QDF.
Okay.
Yep. We try to make everything as modular as possible, but also as interoperable as possible
And I do want to walk through.
So, just to clarify, so if it doesn't say dask, it's going to be single GPU only?
Yeah.
Okay.
Yep.
Okay.
With exceptions, we do have some algorithms that can take NumPy arrays, chunk them up over multiple GPUs. As we're still alpha, we're still kind of figuring out how that is going to be going forward. Right now, dask would be the safe bet.
So I do want to step through one of these notebooks really quickly. So this is going through the Moon's DB scan that Corey just mentioned. So I have this running on my home server. And so you can actually, this isn't any secret sauce. This is actually in the notebooks on the GitHub. So I'm going to execute, these cells. And so this is essentially going through the setup. This is running NVIDIA SMI, which shows you the GPUs I have. So I have 2 older versions, so older than the Volta edition.
It's not my fault.
And then we'll just import some libraries. So this is importing matplotlib. And then from sklearn, we're inputting the make moons. So again, this isn't using any GPUs right now. So the idea here is to show you CPU versus GPU performance with dbScan on this data set. So now we're going to visualize this data, so you'll see the very familiar moons that Corey showed you not too long ago. Again, this is all just CPU. So here we're going to do k-means with scikit-learn on CPU. So we have just invoking the k-means function right here, and then doing your fit predict. These are this was seeded with a non-random, so these are using the means. And we can show, here in a second, when the plots go in, you'll show where the k-means clustering fails. We're also going to do, the agglomerative clustering as well. Again, this is all CPU scikit-learn. And so you can see in these both of these instances, this is showing the motivation for using dbScan, right? Since this clustering approach has failed to capture the distribution of the data. So now we're going to go to dbScan. So scikit-learn.cluster, CPU only, fit predict, and then show here. So this is showing that dbScan is an effective approach to clustering this particular data set. So now we're going to do this within Rapids. So right here we have, focusing on this a little bit more, we're doing import pandas as PD, so that's the standard CPU pandas. And then we're importing cootie, which is the GPU data frame, so that's part of Rapids. So here we're seeing, essentially we're loading in a pandas data frame, and then we're doing the conversion from pandas to GPU. So that takes into effect putting that data from CPU to the GPU, so that you don't have to worry about data movement there. And then that data is into the GPU ecosystem and memory space. And so now we're going to import dbScan from QML. So you can see, this is QML dbScan versus up at the top. I guess I can go down here. The scikit-learn or just dbScan, which is in scikit-learn. So it's compliant in terms of the API. You just have to remember to put Qs in front of things. And now we're going to predict this, fit it, and then plot. And you can show here, this is showing that the GPU version of dbScan gave you a similar result as to what we were expecting. So there's nothing, magic happening beyond here. It's an effective clustering of this approach. So now we're going to benchmark. So we're loading in, to really show the performance of GPU, we're loading in a large data set. So this has 10,000 rows and 128 columns. And so let's do CPU first. So we'll run, this is setting up the dbScan, and then we'll do the fit. And we'll wait. Yeah. So I think this is about 20 seconds. See, if we made them wait like 5 minutes. We just stood in silence. See, this is what you do. This is what you're paying people to do. And I'm forgetting about what I was trying to show, right? So 23 seconds, okay? So now let's do the same thing with Rapids. And then we're going to run the fit predict, and it's done. 310 milliseconds.
So this is calculating a pairwise n squared distance matrix and everything. It's doing this quickly.
So, you know, it's compelling there in terms of just the speed increases that you can get as you're exploring your data and, you know, doing experimentations on it, trying different clustering techniques. Because think about, you know, if you're going through the experimentation of saying, you know, I have this intertangled data set, let me try k-means, and you're waiting 26 seconds or longer in a lot of cases, that's wasted time into really converging on the correct model and the correct tuning parameters to give you the results that you want. Anything else? I think that's about, you know, there's...
So the last time I checked, I only saw a Linux-based distribution. Is that going to probably be the case permanently?
Yeah.
Other than unless we use Docker or something like that?
I think that's safe to say at this point. I don't know of any non-Linux distributions.
Okay.
I think there are people using Macs.
Yeah, Docker would be the best.
Yeah, Docker would be the best.
Yeah. Or what's that? Anaconda, could you do Anaconda via brew? But then the GPU is, yeah.
Okay.
Yeah, you gotta have all three. all three, you know, the GPU, the software, and all that other good stuff in one place.
It's hard to find good Linux machines with GPUs in it, unless you get one custom built. Laptops.
Okay.
Not server, sorry.
We could help you with that.
Yeah.
But you can't take a server with you.
Yeah.
System 7.6 makes laptops so you did with GPUs and Linux.
Linux.
Lambda has a good one that we just ordered. But there's a company called Lambda that has a really decent that we just ordered. But it took a while for me to find that.
Yeah. Doesn't Gigabyte have like really good laptops with GPUs?
Yeah, I know they're increasing.
Yeah.
Yeah, they're not. Yeah, they've got to look for them.
But again, you know, sort of to wrap up, and by all means, you know, ask more questions. But you know, from Corey and myself, again, thanks for letting us talk, and Jason, really appreciate the invitation. Again, this is sort of to stress, this is all open source, so we really highly value contributions and you know, doing issues, doing documentations, and really sort of helping build this out. So I know Corey and I both feel passionately about the mission of Rapids, which is essentially, you know, making data science the speed of thought, and having the power of GPU compute to solve increasingly challenging problems that we couldn't solve before because we had too much data or not enough time to really start to make sense of it. So thank you so much.
Yeah.
Where do you see this fit in like deep learning ecosystem, like for example, going forward?
So we actually have some deep learning folks on our team that are actually trying to bring that deep learning into our ecosystem.
So is it going to be a replacement, a complement? Or?
I think we're aiming for complement everywhere, right? Like I don't think we're aiming to be necessarily a replacement for anything in the ecosystem, right? There's a place for everybody. And to this lady over here that was talking about not being able to have a good system with GPUs, right? If you are able to write your notebooks on a CPU, then when you bring it into the environment where it's effective to have it on a GPU, then you know we want to enable that, right? If you're working in PyTorch, we want to enable being able to come into our ecosystem and play ball, and then go back to PyTorch if you need to.
But you know, I'm probably preaching the choir here too. But you know, to some extent, you have. I feel that some of the kind of marketing and buzz around deep learning has sort of inclined people to think that that's really like the best way to solve problems, or the only way, which isn't necessarily the case, right? So deep learning is a tool to solve problems in a similar way that these traditional machine learning approaches are also tools to solve problems. So right now, you know, machine learning, if you have a whole bunch of unstructured data, you know, if you can't do an autoencoder approach or something like that, then machine learning is really probably the best place to start, and a lot of problems can be solved really effectively by this. And one of the nice things about Rapids that I think makes it so compelling is that it's the entire sort of data workflow that you're dealing with, from ingest to modeling, you know, to go out. And you know, you still have that data wrangling piece to do off of GPU with deep learning, right? So.
So, and QML, all algorithms you basically re-implement, right? So it's not. So, do you think you run into a problem that's like Spark ML has? It's like algorithms there are really cool, right? But there are very few of them.
We've got a lot of people focused on algorithm development right now. A lot of people. I think we're building the primitives correctly, right? We're doing the design so that we can pull the algorithms apart into their little subatomic particles, and then we can combine those together to rapidly make the algorithms, right? And yeah, I have no doubt that it's not going to be too long before we've got mostly replaced. We've also partnered with NVIDIA, the company that's responsible for scikit-learn, so they're on our side helping us do this.
Do you know of any normal Python operations that are not implemented in cootie, for instance?
Yeah, I don't want to come off sounding like every single thing that you do in Python is going to be like done on the GPU, because obviously there needs to be kernels to be able to do the operations, right? So we're trying to replace what we can of the pandas library. It's not complete yet, but we're trying. We're trying to get it there.
Yeah, and I mean, just to add on to that, if you're going through your normal work and you find something that's slow, or you find something in your workflow, you know, that's something to raise an issue to the Rapids team, so they can take a look at it, because you know they don't know what they don't know.
Yeah, exactly. Yeah, we're trying to do what we can to speed things up that are real problems.
Comparing against Spark, and you know, Spark is you know, hooked up with Yarn or job orchestration, and I know you mentioned Dask. I know you played in both worlds.
Yeah.
What is the Python equivalent for a production job orchestrator that would fit with what you're building?
Well, that's Dask. That's one of the reasons why we invested in Dask so heavily. But I also want to make it clear too that you know, we do have an effort underway to put our ecosystem on top of Spark, or underneath Spark, sorry, so that you can interact with Rapids through Spark Optimium, being able to process the data with Spark and having it be processed. So that the hope is that that can do a lot for getting a lot of the existing machine learning algorithms into that infrastructure as well.
And on that point, there's also work in sort of the, you know, even before that in the GPU-enabled databases. So the, you know, if you're familiar with like the Blazing DBs of the world, or the, you know, MapD, which is now OmniSides of the world, which is essentially doing, you know, brute force SQL queries like on GPU. So if you can start to connect to data lakes, then you know you're really sort of transforming the workflow even more, because now you're opening up, you know, fast
Online access.
Yeah, fast online. Yeah.
So you're orienting toward, say, small teams, individuals who are prototyping with this, or?
Oh no, these are definitive efforts that are being made. These are big teams of people that are.
Oh, I mean, as users, the user base. User base.
Yeah, I mean, I would think of the user base of Rapids as the user base of Pandas and the user base of scikit-learn. The idea and the real sort of the selling point, for lack of a better term, of Rapids is all you have to do is plug in a GPU and then, you know, download a driver, right? And then you're automatically getting, you know, 10, 100,000x speed up over what you normally do. So it's trying, you know, you don't have to learn CUDA, you don't have to learn like any of this other sort of low-level programming stuff. You continue to do the exact same thing that you have been doing, with that sort of hook in there that there's 80%, you know, Pandas-like and 80% scikit-learn-like.
And Pandas-like for the data scientist that just needs to get down and dirty with their data, right? And then you've got the C++ API for the engineer that needs to get in there and either add these algorithms to their existing infrastructure or really want to build something different out of it. And then you've got the primitives for the developers that really just need to construct new algorithms, and they need some of the math that we do in the CUDA layer.
Any other questions? All right, well, thank you for coming. Let's thank Corey and Adam one more time.